All right, let's talk about the complement to the dot product, a thing we call the cross product. The cross product is a little bit weirder than the dot product. It's a little bit harder to compute, but it does have some really peculiar and interesting geometric properties that we'll take advantage of several times in this class. Um, the goals of this particular section, section 2.4, are to calculate the cross product of two given vectors. Not as easy as the dot product, as I mentioned. Um, And I'm kind of merging the first two goals. I'm always going to use determinants to calculate the cross product. I'm just going to show you that. You'll memorize it and we'll move on. Um, the cross product sits inside of a much larger, richer theory, what we call sort of integration theory on differential manifolds. And there's just no way that I'm going to try to contextualize the cross product here. It has this nifty little formula that's related to the determinant. It's not actually an accident that it's related to the determinant, but for me to explain that would take several class periods, and that's time that we really can't afford. Find a vector orthogonal to two given vectors. It turns out that the cross product does exactly this. It takes two vectors and produces a third vector that is orthogonal to the first two. Determine areas and volumes by using the cross product. The cross product has this really peculiar relationship to area and volume of certain figures, and in fact that's one of the things that we're going to take advantage of much later in the semester when we do surface integration. And finally, just to have a physical application, the cross product is closely related to the notion of torque. Torque is kind of the amount of twist around a particular axis. And I don't know if you've ever worked on a car or any kind of hardware where you're tightening bolts. Often the bolts are spec'd to be tightened to a certain torque, and that's exactly this physical quantity. Okay, the big idea here is we've got this more complicated, more mysterious vector operation, at least when you compare it to the dot product, that takes two three-dimensional vectors and produces a three-dimensional vector that is perpendicular to both. The cross product technically lives only on three-dimensional vectors. It only works on 3D vectors. But it turns out to work in sort of an intuitive way on two-dimensional vectors if you just append a 0 to each of the two-dimensional vectors and then perform the regular 3D cross product. It actually gives you a sensible result. And then last, the magnitude of the cross product happens to be the area of the parallelogram defined by two vectors. So if I have two vectors, for example, u and v, let me change color here. So if I have two vectors, u and v, and I compute the cross product of u and v, which we don't know about yet, and I take the magnitude of that vector, that equals the area of this parallelogram. And that's really convenient for us. Again, later in the semester when we do surface area integrals, we're going to use this result directly. Let's do a quick flyover of the section and then I'll get to the examples. So heading over to the textbook here. I noticed the textbook was kind of misbehaving during the last lesson when I would switch back and forth from my notes to the browser, and so I'm switching over to Chrome here for a little while. I actually prefer Firefox for a number of sort of philosophical reasons, but if Chrome performs better, we'll stick with it. Let's go to the cross product section, section 2.4. And of course we have the objectives at the top. I'm not leaving out any objectives to start. Look, this section starts off with a formula, with a definition of the formula for the cross product, and it's pretty complicated, and I don't recommend that you memorize it, but just know that this is there and this is the official definition of the cross product. For our purposes in this class, I'm always going to use this determinant process that's defined down here. We'll get to it in a moment. Somewhere down here. Well, let's give this browser a chance to kind of get its life straightened out. Chrome appears to not be doing all that much better than Firefox at the moment. Okay, look, when as I mentioned, the cross product takes two vectors, and through some mysterious process, well, not so mysterious anymore, via this formula, produces a third vector that's actually perpendicular to the original two. And pictorially, what you have are, vector u, vector v, and then the cross product is going to be perpendicular to these two vectors. And this is u cross v. In fact, I lied. This is v cross u. Okay, there's a question here. Should this vector point up, because that's perpendicular, or should it point down? That's also perpendicular. So which one should we choose? Well, it turns out the cross product follows the right-hand rule. So when I write v cross u, you can imagine sort of pointing your fingers along the v direction and your palm towards the u direction, just like the right-hand rule. And then which way is your thumb going to be pointing? It's going to be pointing up, and so that tells me that v cross u is pointing up. On the other hand, if I took this same scenario, in fact, let me make a copy of it. If I took this same scenario and I simply reversed and made it u cross v, let's go back to black here, like that. Then let's see, I would point my fingers along the u direction and my palm towards the v direction, and you kind of imagine a sweeping motion like this, my fingers pointing along u and then my palm facing v. Which way is my thumb pointing in that situation? In that situation, my thumb is pointing down, and so u cross v is actually this vector and v cross u is this vector. They're the same length, but different directions. So it's really important as you work with cross products to kind of have that in your head, that right-hand rule will tell you which direction the resultant vector is going to point. All right, let's go back over here. So there's the formula. Let's talk a little bit about some of the properties of the cross product. There is the cross product following the right-hand rule. So again, u cross v, you point your fingers along u, and your palm points towards v, points in the direction of v, and your thumb points in the direction of u cross v. The cross product is said to be anti-commutative, that in the way that if you reverse the order of the vectors, you introduce a minus sign. So it's almost commutative up to a minus sign. We can explore our understanding of this a little bit if we look at cross products of unit vectors. For example, j cross k, and then I cross j cross k. Let's look at I cross j cross k. I cross j cross k. And I want you to always have this kind of orientation of the axes in your head. There's I, there's j, there's k. All right, j cross k. So my fingers go along this direction, my palm goes along this direction. So which way is my thumb pointing? It's pointing in the positive I direction. So j cross k is I. And then I cross I, this is peculiar. I cross I is actually equal to 0. Whenever two vectors are parallel or anti-parallel, their cross product will be 0. I guess it's also important to note here that the cross product is not an associative operation. What do I mean by that? So if we look at I cross J cross K, actually in this case it probably will be associative. If we look, let's just do this for the heck of it though. I cross J, again we're going to point in our fingers along I, our palms along J, so where's our thumb? Our thumb is along positive K. K cross K. These two vectors point in the same direction, so they're 0. So in this case, it was associative, meaning I could put the parentheses on the right pair or on the left pair and get the same result. That's generically not true for the cross product. Here are some properties of the cross product. We have anti-commutivity up here. The cross product does distribute across vector addition. That's kind of nice. It has this behavior with scalar multiplication. If you have a scalar on one of the vectors, you can factor it out and multiply the cross product like that. U cross the 0 vector is the same as 0 cross U, and that's the 0 vector. It's important to note here, if you see a bold-faced 0, what that means is actually the 0 vector, the vector with zeros as the components. V cross V is equal to 0. In other words, the cross product of a vector with itself is 0. If you combine that with this scalar multiplication result, you see that, in fact, the cross product of a vector with any vector that's parallel will be 0. And then last, we have that U dot V cross W is the same as U cross V dot W. This is called a scalar triple product, and it actually has some connections to volumes of certain solids, which we'll see later. Alrighty. The magnitude of the cross product. So theorem 2.7 is one that I want you to memorize. It's almost, well, it is the complement to the cosine identity from the dot product. So let's see here. I thought I could write on this directly, but I don't think I can. Let me try. Well, we'll let that figure itself out. Okay. So remember that the cross product U dot V is equal to the magnitude of U times the magnitude of V times the cosine of theta. We don't quite have the same thing here, but we have that the magnitude of the cross product is the magnitude of U, magnitude of V times the sine of the angle. What this gives us is sort of a complementary sort of thing. If two vectors point in the same direction, that means that the angle between them is 0 and that the sine of 0 is 0, which means this whole right-hand side is 0, which means the magnitude of U cross V is 0, which means that U cross V is the 0 vector. So the cross product is kind of a test for when vectors are pointing in the same direction. The dot product is a test for when vectors are pointing perpendicular to each other. So they have this sort of complementarity to them. All right, we're getting there. Determinants and the cross product. Okay, I don't want to dwell too much on the determinant. Some of you may have studied this in high school or in other classes. A 2x2 determinant is a rectangle of 4 numbers like this, or a square of 4 numbers. And to compute the determinant of these 4 numbers, you take A1 times B2 minus A2 times B1. That's this guy. Okay, so once you internalize that, that's the 2x2 determinant. We're going to lift ourselves up to the 3x3 determinant. The 3x3 determinant can actually be expanded out into a collection of 2x2 determinants. So the 3x3 determinant, which is a complicated beast here, can be written a little bit more simply as you look at A1 and you cross out the column that it occupies and the row that it occupies, and it leaves behind a little square of 4 numbers. And you take the determinant of that. A1 times the determinant of this is the first term in the 3 by 3 determinant. Now you take A2. A2, cross out its column, cross out its row, and you're left with a 2 by 2 square of numbers B1, B3, C1, C3. And the determinant of that is B1, C3 minus B3, C1, right here. Now, a weird thing about determinants is they have this parity floating around. A1, this slot of the matrix has parity 1. This has parity -1, 1, -1, 1, -1, 1, -1, 1. So all the numbers in a matrix have a parity. So we have to keep that in mind when we're doing these determinants. So when we're doing the middle term here, we have A2, B1, C3 minus B3, C1, and then there's an overall minus sign. No matter how this turns out, you get this minus sign built into the formula. Last, A3 is a positive parity position. A3, cross out its column, cross out its row. What's left behind is this, B1, C2 minus B2, C1, this guy. And this is the formula for the 3 by 3 determinant. I want you to memorize this. Memorize it because it's how we're going to compute, it's how we're going to remember or memorize the formula for the cross product of two vectors. If I have two vectors, u and v, and I want to take their cross product, and remember that order matters. So I have u first cross v second. I take the entries in u and I make them the middle row, and the entries in v and make them the bottom row. And then the top row is always I, j, k. So if you want to compute the cross product, the ith component of this result is going to be the determinant of this little rectangle, this little 2 by 2 rectangle. The jth component is going to be the determinant of these outer columns with a minus sign because of the parity. And finally, the kth component is going to be the determinant of this little 2 by 2 sub-rectangle here, u1, u2, b1, b2. And these three simple calculations are going to give you the cross product. And that's how I want you to compute the cross product. No matter where you are in this class, that's how I want you to do it. It's how I do it to this day, and I've been doing this for a long time. For example, let's look at two vectors. P is -1, 2, and 5. Q is 4, 0, -3, and we want to find P cross Q. So we take P and make it the middle row, and Q and make it the last row, and we start computing. We take I times the determinant of this little 2 by 2 matrix. 2 times -3 is -6. Minus 5 times 0, which is 0. That's down here. And this is going to net out to -6. Now for the middle component, we have a minus sign automatically. We have the j, and we take the determinant of these outer columns. -1 times -3 is 3, minus 5 times 4, which is 20. Let's see, 3 minus 20, that's going to be -17, but there's an extra minus sign, plus 17. Finally, k, we blot out this column, this row, we do this little determinant. -1 times 0 is 0, minus 2 times 4 is -8, and that's the cross product. This cross product, the cross product of these two vectors is -6, 17, and -8. And if you look at this really closely, remember the claim is that this produces a vector that's perpendicular to the two original vectors. How can we see that explicitly? Take the dot product of this vector with, for example, Q. So we get -6 times 4, that's -24. 17 times 0, nothing. -8 times -3, 24. -24 plus 24 is 0. So in fact, P cross Q is perpendicular to Q. I'll leave it to you to check that this vector is perpendicular to P. Of course, I do the easy one with the 0, but if you take this dot product, P cross Q, with just plain old P, you should get 0. All right, let's keep going. Using the cross product, so for example, in this case, let A be this vector, B be this vector, find a unit vector that's orthogonal to both. You can take the cross product, and then you can divide by the magnitude, and that will give you that unit vector. Okay, here's another geometric property of the cross product. The cross product of the magnitude of the cross product is actually the area of this parallelogram. Okay, and this goes back to something that I kind of glossed over. Somewhere up here is, yes, this very important sign identity, which follows just by brute force. You take U cross V, you square it all out and simplify, and you end up with this expression. So we know that U cross V squared is equal to magnitude U squared, magnitude V squared, sine squared, and then take the square root, and everything works out. And then because we're taking the value of theta between 0 and 180, that makes the sign behave properly. So because that makes the sign positive. All right, so we keep this identity in mind and pay close attention to this magnitude of V sine theta, and go back down to this parallelogram thing. If we have the parallelogram defined by V and U with the angle theta between these two vectors, the height of the parallelogram is given by just the length of this vector times the sine of theta, right? Basic trigonometry. So the area of the parallelogram is the base times the height. That's the formula. What's the length of the base? It's the magnitude of the U. What's the height? It's the magnitude of V times sine theta. And that is equal to the magnitude of U cross V by the identity up above. So this is a really useful geometric identity that we'll see later when we do surface integrals. Further, it can be used to quickly find the area of a triangle, because the area of the triangle that's defined by V and U, in other words, the triangle that goes has this side V, this side U, and this side U minus V, the area of that triangle is exactly half of the parallelogram. So if you're looking to find the area of a triangle using the cross product, you can just use the magnitude of the cross product divided by 2. Another geometric identity, this one related to volume, is a thing called the triple scalar product. And if we have a, looks like we don't have, yeah, there we go. Okay, if we have 3 vectors, U, V, and W, arranged like this, they define this sort of slanted box kind of object. And if you take the absolute value of U dot V cross W, you actually get the volume of this slanted box, which is pretty cool. So lots of geometric stuff that you'll be seeing later. Let's keep going here. And last, not least, the torque. This is kind of a measure of the twisting motion on perhaps a screw or a bolt or something like that. You can imagine applying a wrench to a bolt and turning it with a certain force. The longer the wrench, the more force, or the easier it is to apply additional torque. And so the formula for torque, which is a vector value quantity, is just the displacement vector where you're applying the force. You know, how far are you from the point where you're rotating around, and then how much force are you applying. If you can figure out these 2 vectors and you can do the cross product, that'll give you the torque vector. So the classic example is the wrench on a nut. Here's a wrench, and we're applying a force of 6 newtons in a particular direction, and then the length of the wrench is 0.15 meters, and you figure out the 2 vectors, you take the cross product, and that gives you the torque. Okay, so that's our rapid fire sail through the cross product. Again, the 2 big takeaways from this section are how to compute the cross product using this determinant idea, this 3x3 determinant, and we'll do a few examples in a minute. And the sign identity, that the magnitude of U cross V is the magnitude of U, magnitude of V times the sine of theta. And I guess another big takeaway is that U cross V is a vector that's perpendicular to both U and V, and it follows the right-hand rule. Okay, let's look at our first example, problem 188. And this is really just understanding some of the algebraic properties of the cross product. Alrighty, so let's break this out a little bit. We're going to work from the inside out. We'll do this J cross at the end. If you look really carefully, I know it gets a little bit messy. The cross products happen before the additions. So just to make that clear, I'm going to put some groupings in here. I'll make them red. So I'm going to group those guys together, and those together, those together, and those together. And I'm going to figure out each of those before I proceed. So this is J cross. Now inside, what's K cross J? Well, imagine pointing your fingers along K and your palm towards J. Which way is your thumb pointing? Towards the positive x-axis or the negative x-axis? So I'll pause here. You can pause here and you can think about that. So your fingers are pointing along K. Your palm is pointing along J. In the usual orientation, and let me draw them over here just so that you can kind of remind yourself. This is the positive I direction. This is the positive J direction. This is the positive K direction. So I want you to stare at those three axes, and just in case you're wondering, J is kind of pointing into the board or into the screen. I is lying horizontally on the surface, and K is lying vertically on the surface. So J is kind of penetrating into the screen, and it's positive inside the screen and negative coming out of the screen. Hopefully that's clearer. All right, K cross J, so our fingers are pointing, the fingers of my right hand are pointing along the K direction, and my palm is pointing towards the J, positive J direction. Which way is my thumb going? Pause. So if you are unpausing now, your thumb is pointing in the negative I direction. So this resolves to negative I plus 2 times whatever J cross I is. So let's repeat the experiment. Now the fingers of my right hand are pointing along positive J. My palm is pointing along positive I. My thumb is pointing, pause, along negative K. So that takes care of the first two. Let's do minus 3 times J cross J. All right, J cross J, 0, right? Because J is parallel to J. So we'll put a 0 in there. And finally, plus 5 times I cross K. All right, my fingers pointing along positive I, my palm pointing along positive K. Which way is my thumb pointing? Pause. My thumb's pointing along negative J. Notice also I'm using the scalar identity. I'm taking this 2 out of the cross product, the 3 out of the cross product, the 5 out of the cross product. Let's look at what's left behind and see if we can't make sense of this. Let's take J cross. We have negative I minus 2K minus 5J. All right, we want to now finish the cross product. Remember that the cross product distributes across addition. So I can write this as negative J cross I minus 2J cross K minus 5J cross J, like that. It's also super important to notice that this J always appears first because we distributed it from the left. So it's going to appear on the left in each of the terms that it distributes on. If, on the other hand, this had been this quantity cross J, then J would have distributed on the right and would have appeared on the right in each of the terms. Cross product, not commutative. You've got to pay attention to the order. Let's repeat this process. J cross I, fingers along positive J, palm along positive I. That's going to give me negative K. Minus 2, J cross K, fingers along positive J, palm along positive K, thumb, positive I. And finally, J cross J, 0. All right, we're getting there. We have K minus 2I. Oops, K minus 2I, like that. And if we wrote that in component form, that would be negative 2, 0, 1, just like that. All right, I want to do an aside here. These calculations are complicated. It's really easy to make a mistake when you're doing the cross product, and wouldn't it be nice if we had some tool at our disposal to help us compute cross products and check our work? Doesn't mean that you're not responsible for being able to do these in your head, but I also want you to have all the tools at your disposal to be able to check your answer and to do more complicated work perhaps later. And so I'm going to introduce the second of the technological tools that we'll be using this semester. You've seen me hint at GeoGebra. I'm going to introduce something called Sage. Sage is a computational engine. It's a computer algebra system. In keeping with my philosophy about technology, it's a system that is free. You can use it wherever, whenever you want. You don't have to pay for it. And the Whitman College Math Department actually runs a free Sage server, and I'm going to make a separate companion video that will help you get set up. For now, just kind of watch me do the calculation and know that these computational tools are out there. This is not by any means the only computational tool at your disposal. If you're comfortable with Mathematica, Mathematica is more than capable of doing cross products, dot products, other kinds of calculations. Feel free to use that. Wolfram Alpha, limited, but can do cross products and dot products and many of the calculations that we'll be doing here. But again, my philosophy is to kind of provide you with free accessible tools that you can use forever, right? When you leave Whitman College, you're not going to take Mathematica with you, and Mathematica is pretty darn expensive. So let's look a little bit at Sage here. So Sage, you know, it does have a bit of a learning curve. I'm going to create a new little Scratch document here. I'm going to call it section 2.4, the cross product. And this is going to be a Sage worksheet. And I start out with this just empty command prompt. What I'm going to do is create 3 vectors. I is going to be the vector 1, 0, 0. And so you have to learn all this syntax, and I'll point you to some tutorials if you're interested in this. J is going to be 0, 1, 0. And finally, K is going to be the vector 0, 0, 1. And once I've typed the 3 commands that I'm interested in, I can just hit Shift-Enter. And now these 3 variables actually contain these 3 vectors. And I can verify that if I just look at the vector. For example, show me I. So I say, hey, Sage, what does I look like? And it gives me a nice version of what the vector looks like. Now, I can do cross products with this. For example, I can do I dot cross product J. Okay, so my fingers point along the I direction. My palm is pointing in the positive J direction. Which way is my thumb pointing? Positive K. So let's run this. And in fact, we do see that this is 0, 0, 1, aka positive k. So we can check our work here. And in fact, if we go back to this really complicated one, we can do J cross product. What did we have? We had K cross product J plus 2 times J cross product I minus 3 times J cross product J plus 5 times I cross product K. Let's check that really carefully. We had J cross the quantity, K cross J, yes. 2J cross I, yes. Minus 3J cross J, minus 3J cross J, good. Plus 5I cross K, 5I cross K. Executing this, we get negative 2, 0, 1, and that's the answer. So this is a nice, efficient way of checking your work, and not only can it work with explicit vectors with constants, but can actually work with vectors that have variables in them, and we may talk about that in a little bit. All right, let's go on to the next exercise, problem 192. Okay, in 192, let's see, find the unit vector W in the direction of the cross product U cross V. So we've got these two vectors, OP and PQ, where P and Q are given by these points, and we want to find U cross V. Well, first thing we have to do is figure out OP and PQ. OP, of course, is just the vector that goes from the origin out to P. So we can write U as the vector negative 1, 1, 0, like that. And V is the vector that goes from P to Q. And do you remember how to calculate that? We look at Q minus P, P, negative 1, 1, 0, like that. And we subtract component-wise. So that's a minus sign right there. 0 minus negative 1 is 1. 2 minus 1 is 1. And finally, 1 minus 0 is 1. That's a nice little vector. Okay, U cross V. Let's figure out U cross V. Again, we're always going to use the determinant method. So here's our first exercise that has us doing that. U cross V, so the next row is going to be U, the first vector, and the last row is going to be V, the second vector. And I always just proceed the same way. I have I times the quantity. The determinant of this little 2 by 2, 1 minus 0 is 1. Always minus J. It comes with the formula. So we look at the J column here, and we want the determinant of these outer columns. Negative 1 times 1, minus 0. That's minus 1 in the parentheses. And we'll simplify this later. Plus K times the quantity and the determinant of this little 2 by 2. Negative 1, minus 1, negative 2. In component form, the I component is 1, the J component is 1, and the K component is negative 2. So that's the cross product of U and V, and we're calling that W. I'm sorry, we're not calling that W because you're asked to find the unit vector W in the direction of the cross product. How do we turn that into a unit vector? We divide by its length. So if we divide by the magnitude of this vector. The magnitude is 1 squared plus 1 squared plus negative 2 squared. This is all square root of 6. Now that's W. If we divide by the square root of 6, that is the That's the unit vector. Let's just real quick, just to kind of let you know that we're going to check our work. There are a couple ways we can check. Number one, this vector should be perpendicular to this vector and this vector. Let's do the dot product of this vector with u. When we do the dot product, we see -1, 1, and 0. That adds up to 0. Great. And we do the dot product here with this vector v, we get 1 plus 1 minus 2, also 0. So w is a unit vector and it's perpendicular to both u and v. I recommend always checking that orthogonality relationship, at least during this section when you're first learning how to do the cross product. It's so easy to make a mistake, and that's an easy way to catch an error. Let's look at 198. In 198, you're just asked to calculate the determinant. So let's do that. Just kind of driving home this process. You want to make it sort of habitual, develop that muscle memory. So we have I times the quantity, this determinant here, -3 minus a -24. So that's going to be, careful, 27. Minus j, it's always minus j. And then the outer determinant, 0 times -1 is 0, minus -4 is 4. And then finally plus k, 0 times 6 is 0, minus 3. And then in coordinate form, that's 27, -4, -3. And again, if you want to check really quickly, this should be perpendicular to both of these vectors. If we do the dot product of this with this first row, we get 0, minus 12, plus 12. That's 0. Awesome. And if we do the dot product of this guy with the second row, we get 27, minus 24, plus, wow, did I make a mistake here? Mayhap I did. Let's double check that for a second. 27. Do I like 27? -3 minus a -24. -3 minus a -24. That's a 21. See what I mean? It's so easy. Let's see if that fixes it. So we want to do the dot product of this guy with the second row, 21 minus 24 plus 3. There we go. Yep. Easy to make a mistake. All right, let's throw this guy in there, 205. 205. Use the sine and cosine of the angle between the two non-zero vectors, u and v, to prove Lagrange's identity. So this is a proof style problem. And what are some of the things that we know? Well, we know, right? It's you know, I'm going to do this problem. I'm going to do it really quick, and it's going to seem like, well, how the heck am I supposed to know how to do that? You know, I don't want to belabor the point here, but what you want to do is write down just lots of facts, things that you know, and see if anything rings a bell. So you start writing down facts about the dot product and the cross product, and eventually you're going to get these two facts written down on your scratch paper. And this fact from the previous section. And you're going to stare at that and you're thinking, well, you know, if I squared this, I would get something that looks like this, and I would also get things that look like this. So maybe if I squared this, and you know, if I squared this, I would get a thing that looks like this out of here, and I'd also be getting stuff like this. But you know, the sine and cosine, there's no sines and cosines in here, so I don't really know what's happening there. Like, what's going on there? But you know, maybe I'll just try it and see what happens. So maybe I'll square both of these and I'll add them together. And if I do that, what do I get? I get magnitude of u cross v quantity squared is magnitude of u squared magnitude of v squared sine squared. And of course, u dot v quantity squared is magnitude of u squared magnitude of v squared cosine squared. Now, maybe I wouldn't have figured out to add, but I square both equations and I get something like this. And then I'm staring at this and I'm like, man, how am I going to get here? Well, I see the sine squared and the cosine squared, and that should sort of jump out at me and say, you know, sine squared plus cosine squared equals 1. And if I'm trying to get rid of sine and cosine because there aren't any in here, maybe somehow if I add these two equations together, I can use that identity to eliminate the sines and the cosines. So I'm going to add these two equations together. Oops, sorry. On the left-hand side, we just have u dot v quantity squared. On the right-hand side, I have u squared v squared sine theta plus u b cosine squared theta, like that. And notice, right, I've got this common factor here and here. And then I have the sine squared and the cosine squared, so I can apply the Pythagorean identity, and the right-hand side simplifies dramatically, like that. Cool. What I've just shown is that this equals this. Can I get from here to here? And the answer is, of course, yes, if I subtract this term from both sides. And there's the identity. So again, I did this relatively quickly. I would expect you to kind of take some time and maybe work on it for a little while and then come back to it later and read the section and come back to it later. I wouldn't sit here and bang my head against it for a half hour. That's usually not productive, at least it's not how my brain works. I usually kind of have to absorb the problem and think about it for a while and go away and do something else and come back and just kind of let it percolate. But everybody's mind is different, so you do what works for you for hard problem solving kinds of things like that. Let's move on to problem 212. Problem 212. This is some area and geometry kinds of questions. So we've got some points, A, B, and C, and we want to find the area of the parallelogram A, B, C, D. All right. Look, these are points in 3 dimensions. I don't really know, I'm not going to bother plotting them, but I know that from some perspective, it's going to look roughly like this. Oops. I know that from some perspective, this might be A, the point A, this might be the point B, this might be the point C, and then out here, kind of the ghost of point D here, and that completes the parallelogram. So this side here is the vector AB, and this side here is the vector AC. Helps to draw a picture. You want to find the area of the parallelogram with adjacent sides AB and AC. We know that the area of this parallelogram is going to be given by the magnitude of the cross product of these two vectors. So let's find AB. AB is point B, 0, 1, 2, minus point A, 2, negative 3, 4. 0 minus 2 is negative 2. 1 minus negative 3 is 4. And 2 minus 4 is negative 2. So, and then let's do the other guy, A, C. That's going to take the point C, negative 1, 2, 0, minus the point A, 2, negative 3, 4. And doing the subtraction, negative 1 minus 2 is negative 3. 2 minus negative 3 is going to be 5. And 0 minus 4 is going to be negative 4. And I'm just checking my work here on my notes. Yep, that's correct. Alrighty. Well, these are the vectors that correspond to these two sides of the parallelogram, and we're going to use the fact that the magnitude of the cross product is the area of the parallelogram. So AB cross AC is, always use this determinant identity, IJK. We'll put the first vector, negative 2, 4, negative 2, and the second vector, negative 3, 5, negative 4. Now, since we're only interested in the magnitude of this vector, it doesn't matter which order you do this cross product, because in the end, the magnitude of one order is just going to be the same as the magnitude of the other order. Alrighty, let's do our mnemonic. I times the quantity, negative 4 minus negative 10. Boy, oh boy, negative 4 minus negative 10 is going to be 6, minus j, quantity. Negative 2, negative 4 is 8, minus 6, that's 2, plus k times the quantity. Negative 2 minus negative 12, so that's 2. And in component form, that's 6, negative 2, 2. Let me check my work here, make sure I'm not messing up. Looks like I got a negative 6 on the first one here, so let me double check. Negative 6, so that's, sorry, that's 8. Yeah, 8 minus 6. Wow, that's just flat out wrong? Yes, I think that's just flat out wrong. Okay, negative 2, negative 4 is 8 minus 6. Looks like that's 2. All right, my notes are wrong. See what I mean? It's super easy to make a mistake. Let's just go over to Sage and double check this, shall we? So let's make a couple of vectors here. Let's call AB the vector. AB is the vector negative 2, 4, negative 2. And AC is the vector negative 3, 5, negative 4. Like that. And then let's do AB dot cross product AC. And we get negative 6, negative 2, 2. Negative 6, negative 2, 2. So yes, I'm just losing my mind here. Alrighty. Okie dokie. Yeah, I already see what I was doing wrong here. So cross out this column, work on this little guy. 4 times negative 4 is negative 16. Minus negative 10. Negative 16 minus negative 10 is negative 6. All is well. All right, let's compute the magnitude of this thing, because that's going to give us the area of the parallelogram. The magnitude of AB cross AC is 36 plus 4 plus 4, square root. That is 44, the square root of 44, which simplifies to 2 root 11 if you are so inclined. Okay, that's the answer to the first part. Part A. What about part B? Part B says find the area of the triangle ABC. ABC. So that's this triangle right here. Well, what do you notice about the area of that triangle? It's half the area of the parallelogram. So the answer to part B is a pretty straightforward one. We'll take the area of the parallelogram and divide by 2. And that's the square root of 11. Part C, find the distance from the point B to the line AC. That's this distance right here. And recall that that is the magnitude of A times B. Let me not put that in there. That is the magnitude of AB sine theta, like that. On the other hand, what do we know? What identity do we have for for the cross product? We know that the magnitude of the cross product is equal to magnitude of u, magnitude of v sine theta. So we're looking for v sine theta. So what we should really do is look at the magnitude of the cross product divided by the magnitude of AC. All right, so we want, for part C, we know that the magnitude of AB cross AC is equal to the magnitude of AB, magnitude of AC times the sine of theta. And of course we're looking for AB sine theta, so let's solve for that. Like that. And we have most of what we need. We know that the magnitude of AB cross AC right up here is 2 root 11. What's the magnitude of AC? Well, let's go back up and remind ourselves what AC was. It was this thing. So that's 3 squared plus 5 squared plus 4 squared. 3 squared plus 5 squared plus 4 squared. That's going to work out to what? 9 plus 25 is 34 plus 16, 44, 50. That's going to work out to be 50, and then square root. And 50 can be written as 5 root 2. So we have 2 root 11 over 5 root 2. And we could leave it like that, or we could even simplify further. I'm just going to stop there. So the height of this thing, this distance from B to the line along the base AC is 2 root 11 over 5 root 2. This is the distance from B to AC. All right, 221. In 221, we have a number of proofs that we're going to do. I'm not going to do all of these. I'm just going to kind of talk you through how they might go. Some of them are quite involved in terms of the algebra that it would take to complete them, and I'm not going to do that here in this context. Let's look at, say, part A. So how can we prove that u cross u is equal to 0? Well, we could let u equal u1, u2, u3. We write it in component form, and then we can literally just compute the cross product using the identity. And again, I always use the determinant. And if we write it like that, we have I times u1 u3 minus u3 u1 minus j u1 u3 minus u3 u1 plus k u1 u2 minus u2 u1. That's the zero vector. And this bold-faced 0 actually means 0, 0, 0. So that identity is true. For part B, I think what you'd be left doing is actually writing out U as U1, U2, U3, V, V1, V2, V3, W, W1, W2, W3, and working all of this out and combining it so that you end up with the identity. And similarly with the rest of these guys, so I'm just going to write PP MNA, which stands for pages and pages of mind-numbing algebra. That doesn't mean it's not worth doing, it just means I'm not going to do it here. And similarly for these others, although perhaps for C, we can make a bit of an argument if we go look at the identity way up at the top, the definition of the cross product. If you imagine that there's a C on this vector, we have a C here, a C here, and a C here. Or if you put the C on U, where we have a C here, a C here, and a C here, you can imagine that they end up being the same. So maybe you can argue that from a little less algebra. And then for this one here, I think you're back to just doing PPMNA, pages and pages of mind-numbing algebra. All right, problem 236. This is a physics application, a torque problem. And for our purposes, this is mostly about just expressing the two vectors, the force vector and the displacement vector. Because remember that the torque tau is the displacement vector crossed with the force vector. So we have to figure out what these two vectors, what the coordinates are of these two vectors. So let's give ourselves a coordinate system here. Let's do the following coordinate system. I'm going to take so we need a coordinate system in order to express our vectors. I'm going to take this to be the I direction. I'm going to take this to be the K direction, and then in and out of the screen is the J direction. That's our usual approach. So in this context, the force vector is 20 times negative K because it's pointing downwards. We have to figure out what this vector is. It's just to remind everybody, these torques are in foot-pounds. It says express your answer in foot-pounds, which means we want everything in terms of pounds and feet. This side is 6 inches, which is a half of a foot. And we need to describe this vector R. It's a vector that looks like this in the IK plane, and it makes a 40-degree angle right here, and its length is 1/2. So how might we express that? We're going to express that R vector as, let's find this angle right here. This, if the whole angle is 180 and this is 40, then this is 140. So what's this component? It's 1/2 cosine of 140. And what's this component up here? It's 1/2 sine of 140. So that's what R looks like. All right, you want to do the cross product on this to figure out the torque. So let's do that. R cross F. Again, the order is important, right? The torque is defined to be R cross F. So we're going to take R as the first vector and F as the second vector, I, J, K. R is going to be 1/2. In fact, we can just pull the 1/2 out front and just put the cosine of 140 here and the sine of 140 here. What goes in this slot? 0. It has no J component. All right, and the force is 0, 0, -20. Love having zeros in my determinants, in my cross products. 1/2 overall outside, and then we'll take I times the quantity. 0 times 0, subtract, we get 0. Minus J, remember, always minus J. J here is -20 cosine 140. Minus 0. Cool. Okay, and K, 0. So plus K times 0. All right, let's simplify this a little bit. We've got our 1/2 out there. I'll just carry that along for the moment. This is a negative sign and negative sign, so this is 20 cosine 140 times J. All right. Simplify that a little bit more. 10 cosine 140 J. And then maybe we'll go ask Sage or Google. Let's ask Sage what the cosine of 140 is. So just like everything else, Sage works in radians. So we need the cosine of 140 times pi over 180. That's how we convert from degrees to radians. And if I hit enter here, I'm going to get a less than useful quantity here. Sage tries to keep everything symbolic unless forced to do otherwise. It has a little function built in, the n function, which turns anything inside of it to a number if possible. And I get -7.66. So this is actually -7.66 J. All right, does that make sense? Well, that's the amount of torque that's pointing in this direction. And if we take, if we do the right-hand rule and we look at the direction that R is pointing and the direction that F is pointing, and we look at the cross product, our thumb is going to be pointing in the negative J direction. So that works out. All right, let's do 242 here. 242 is another application, solar panels on the roof. make some room to work here, and I suppose maybe shrink this down a little bit, get it all on the same screen. Alrighty. So we got a solar panel on the roof. According to some kind of mysterious coordinate system, the point A is at 800, B is here, C is here, and D is here. If you study these points long enough, you can kind of figure out the coordinate system, but it's not super important at the moment. The first thing they want you to do is find a vector n that's normal to, perpendicular to the surface of the solar panels. Well, if we can figure out this vector AD and this vector AB and take the cross product, that's going to give me a vector that's perpendicular to the solar panel. So let's do that. Let's compute AB and AD. So the vector AB is just the point B minus the point A. Eight minus 8 is 0, 18 minus 0 is 18, and 0 minus 0 is 0. So AB is that vector. And let's find AD. AD, we want the point D, which is 0, 0, 8. And we want to subtract the point A, which is 8, 0, 0. And we get negative 8, 0, and 8. All right, we want to find the cross product. N is going to be the cross product of these two vectors. Back to our determinant mnemonic. And what's the order? It's AB cross AD, so we'll take AB first, 0, 18, and 0, and AD, negative 8, 0, and 8. And we do this cross product, I times the quantity 8 times 18. Actually did this one in advanced too, so 8 times 18 is going to be 144. Minus j times the quantity, I get 0 minus 0, which is 0, plus k times the quantity, 0 minus a negative 144, so 144 it looks like. And so our normal vector, our perpendicular vector in component form is 144, comma 0, comma 144. All right. So if we assume a unit vector S points towards the sun at a particular time of the day, and that the flow of solar energy is this vector F 900 times S, find the predicted amount of electrical power the panel can produce. This is given by the dot product of the vectors F and N. So if we take F and we dot it with N, so this is part A up here, but part B, if we take F, which we can write in component form like this, 900 times S, actually 900 over root 3 times 1, 1, 1. Notice I factored those scalars out front. And then we can write n, again, factoring that scalar out front, 144, 101, like that. And we can compute the dot product. F dotted with n is just going to be the dot product of these two vectors and times the product of these two scalars. 900 times 144 over the square root of 3 times the dot product of these two is 2. And that pretty much settles that. All right, determine the angle of elevation of the sun above the solar panel. Express your answer in degrees rounded to the nearest whole number. Hint, the angle between the vectors n and s and the angle of elevation are complementary. So we can figure out the angle between the vectors n here and s here, then we can figure out the angle of elevation. Now, the scalars don't matter here, so make your life simple. Let's look at f prime. We'll just call it 1, 1, 1. And n prime, 1, 0, 1. And let's find the angle between these two. Well, we can do that using the dot product identity, or you could use the cross product identity. It's not super important, either one. I think the dot product identity is a little bit easier. So note that f prime dot n prime is equal to the magnitude of f prime, magnitude of n prime, cosine of the angle between the two. So let's look at f prime dot n prime, that's just 2. And then let's divide by the magnitude of f, which is root 3, and the magnitude of n, which is root 2. And that should equal the cosine of theta. And we can then solve for theta as the arc cosine of 2 over root 6. That root 3 times root 2 turns into root 6. And maybe we can hop over to Sage one last time and ask ourselves, what's the arc cosine of 2 over the square root of 6? And once again, it doesn't want to give it to us in decimal form, so we're going to force it by putting this n function around it. And I get 0.615, so that's 0.62 radians. That's approximately, let's go back to Sage and figure out what that is, times, let's do n, 0.62 radians times 180 divided by pi. We get about 35.5 degrees. And remember that the angle of elevation of the sun is complementary to this, so the angle of elevation of the sun is 90 degrees minus 35.5 degrees. That's going to be what, 54.5 degrees? So that's a sun that's relatively high in the sky. Okay, suggested exercises, essentially all of the exercises with the exception of 223 through 226. Why am I excluding those? If you go look at them, they're talking about a topic from linear algebra, and it's not that I'm opposed, but I just don't want you focusing on that particular topic, the topic of linear independence or linear dependence. It's not something that's going to come up in the class, and if it does, I'll cover it at that point. So all of the exercises except for those exercises, again, don't do them all, just do a sampling of them from each of the various sections. Do enough of them so that you feel confident, and when you feel confident, go over to WebWork and take the assessment for Chapter 2, Section 4, the cross product. Thanks.